Good afternoon, everyone. This is Pengchuan Zhang. I'm currently a research scientist at Mditer AI, and today I'm very happy to share with you this tutorial of vision language pre-training for object detection. And first, thank Jianwei for the good starting point of fine-grained vision language pre-training for fine-grained understanding. So the reason why we care about vision language pre-training for object detection is that we want to achieve something called object detection in the wild. So typically, academic people are chasing some benchmark like Microsoft Coco or get higher and higher. We call this object detection in the lab. But in practice, we want to solve real world problems. Like we want to detect dogs and people in thermal images. We want to detect the wildfire in California mountains. And in this case, we want to detect different kinds of fishes in occurring. So this kind of problems is real problems, but it's challenging because we face very different domains like thermal images. We face different concepts like smokes or this jellyfish, which is not covered by academic data sets. So as shown by examples here, so you can see that the main challenge of object detection in the wild is that first, it's open vocabulary. We may face unseen concepts, novel concepts. Second, that this is intrinsically a zero-shot and few-shot transfer learning problem, because in real-world tasks, we have very few or even zero task-specific annotations, but we want to do good on this task. The third one is very challenging domain adaptation. As we can see in this in the examples, we may want to work on thermal images. We want to work on images taken from underwater environment. These are image domains that's different from the academic data set, which is very standard and good quality. So the way to overcome this challenge is that we think that vision language pre-training is a good approach to overcome this challenge and achieve object detection in the wild. The main idea is that first, object detection is intrinsically a vision language grounding task. Like in the last talk, image classification is a vision language retrieval task, and here we can argue that object detection is a vision language grounding task. The second one is that if we view object detection as a vision language grounding task, then we can pre-train the grounding model with both region level annotation data, like detection data, grounding data, but also the most important part is that we can train the model with weakly image text paired data without box annotation. These are the data that can really scale up and give us good coverage of the concepts. So here is an overview of existing work in this domain. We categorize this work in two angles. In the horizontal angle, we have VLP for region level classification, which is mentioned by Jianwei just now. The representative work is VLD region Glib. In this VLP for region level classification work, essentially it need a pre-trained box proposal, and then you try to leverage the image classification or image text retrieval model to do the understanding task or classification task for you. On the other side, we have this vision language pre-training for end-to-end detection. There's also another work here, like Mditer in last year's ICCV and the Glib for this year's CVPR. Also, we have another work coming, and they are on archive like Glib V2, Fiber, Fundit, and Mditer. The vertical axis is generic box proposals and the text-guided box proposals. This concept is important in the way that for object detection, so the generic box proposals means that this kind of models have makes the assumption that we have a generic box proposal, And then we just want to classify each proposal into different concepts. But you can imagine that if we want to achieve object detection in the wild, maybe your generic box proposal need to be very strong because it needs to cover a lot of concepts. This is kind of quite challenging. So you may even kind of challenge the assumption that whether there is a generic box proposal or not. So this is a reason why we have another kind of work, which is text guided box proposal, which means that, okay, the box proposal is not generic, but it's determined by the text prompt that you provide. So the model essentially kind of take input of your intent as the text prompt and then just propose or just detect the concept that you are interested in. And in this kind of work, this object detection in the wild have some related topics like the zero-shot object detection. So there are some there's a long history of zero-shot object detection there. But as we mentioned in the classification topic here, what we are doing for vision language pre-training for object detection is essentially kind of, you can think that it's not zero-shot object detection because zero-shot object detection focuses not on novel concepts. Your pre-training do not really observe this concept, but you want your model can generalize to those concepts. For vision language pre-training for object detection, in fact, the large-scale image text pairs contains a lot of concepts already, including the concepts that you may see in the downstream task. So essentially, in vision language pre-training for object detection, we care more about the setting that it's data efficient. Like for downstream task, you do not need any data annotation, task-specific annotation to do the downstream task. In that case, we typically call that it's zero-shot transfer instead of the traditional zero-shot object detection. There's another string of work which is open vocabulary object detection, which is covered by Jianwei already. Another string is phrase grounding, referring expression comprehension, and then we also have a number of work called general purpose vision system like Unite, GPV, Florence, Scattle, COCA. This kind of work are all related here. For this talk, I will mainly just cover two works. One is this Mditer, one is Glib. So first, let's look at kind of Mditer, which is kind of the first work that's do text-guided detection or object modulated detection. This work is from NYU and Facebook. So first, what is modulated detection? In fact, modulated detection is defined as free-form text conditional detection. The main idea is that we want to avoid using fixed predefined label sets for the detection task. Instead, we want to detect anything that can be found in the free-form text associated with the image. Crucially, we only detect objects that are related to the text query, and we train this entire system in an end-to-end manner so that the object representations can reflect the need of the downstream tasks. Due to this formulation, Mditer is able to leverage the compositionality of language to generalize to unseen combination of object classes and attributes, which we can see in this image. Although the concept of pink and the elephant has already occurred in the pre-trained data set separately, but they are not occurred together never. But the Mditer model is able to put this concept together and detects the novel objects, the pink elephant, which is not possible to achieve trivially with existing method using frozen pre-trained detectors. So this Mditer model is built upon the Diter architecture, which is a transformer encoder decoder architecture trained to do object detection in an end-to-end manner. It casts the problem as a set prediction problem, where the set of objects is predicted directly in parallel. It uses a bipartition matching to compute the optimal alignment between the predicted and the ground truth objects. But the same, but as with kind of the same with the traditional detection models. Mditer is supervised using L1 and generalized IOU nodes for box regression and a softmax classification nodes for neighbor prediction. So you can see that this box regression part is responsible for localization, and the neighbor prediction part is responsible for understanding or kind of this classification. Mditer converts this Mditer model into a free grounding model by introducing the language encoder, Robotan, and replacing the neighbor prediction nodes with the soft token prediction nodes. So you can see here in Mditer, the nodes is box regression, which is kind of the same with Mditer model, but there's a novel node which is soft token prediction. So the important difference between the soft token prediction and the traditional classification nodes is that the predicted boxes are no longer supervised with a fixed neighbor set, but are trained to predict the span in the text that corresponding to the 2x box. For example, here the first box is corresponding to the cat, so the the first box, the soft token node is not trained to kind of classify this box to a cat concept, but just to train this box to kind of predict, okay, it's corresponding to the first and the second token in this sentence. So Mditer is pre-trained on image text pairs where the associated bounding boxes are also available. Specifically, Mditer merge data in Flickr certificate entities, which is a free grounding data set. RefCoco, RefCoco Plus, RefCoco G, which are data sets for referring expression comprehension, and the VL genome dense captions, which has region level caption annotation, and finally GQA data set with its associated box annotations. So this kind of merged data set result in 1.3 million another image text pairs with bounding boxes annotations. And here we show kind of one kind of data example in the pre-training data. Essentially, it's a free grounding data set. So because the Mditer is trained with kind of this kind of large scale grounding data set, definitely it will kind of perform very good on kind of this grounding task. Like the free grounding task on Flickr certificate, the task is that for each sentence containing one or more phrases, which may be interrelated, the task is to provide a set of bounding boxes for each phrase. For example, for the first image, so the sentence is one small boy climbing a pole with the help of another boy on the ground. So the task is to accurately locate these two boys. So the Mditer, due to the large scale pre-trained grounding data sets, Mditer kind of reach a very high kind of is kind of a breakthrough in the Flickr certificate, greatly improve the performance over the previous SOTA. Also, another kind of related task is the referring expressions, like in RefCoco, RefCoco Plus, and RefCoco G. So here, for the referring expression task, given a single phrase, the task is to provide a bounding box for this phrase. And the Mditer also have very excellent performance on this task due to the large scale grounding pre-training data sets. So Mditer also show promising few shot detection performance on average. So more specifically, compared with Mditer, you can see for the third row to fourth row, which is not pre-trained on the 1.3 million grounding data. Mditer in the last 3 rows shows much better results in the small data region, so in the low data region. However, the best performance of Mditer is still far away from the standard masters and baseline. So this kind of come to the limitation of Mditer. So first, the intrinsic limitation of Mditer is that it's really not for zero-shot detection. So in the Mditer data, it is never the case that the text does not corresponding to the image. This means that the model that the Mditer have trained will always try to find an object, like in this picture. So if you give the kind of give a text Kona, although Kona is not in this image, but the model will try to just find something that's similar to Kona, regardless of there's no Kona at all. So the second problem is that the pre-training data does not scale up in Mditer. So as we have already seen, the pre-training data in Mditer are all another image text pairs with box annotations. They kind of nearly gathers all public available grounding data. But this data scale, 1.3 million, is still very small scale, and it is difficult to further scale up because the box annotation requires in the grounding data is very kind of expensive to annotate. Then we go to the next work. So this is grounded language image pre-training. This work is from UCLA, Microsoft, University of Washington, Wisconsin, and IDEA. So the Glib work, this Glib work, in fact, builds upon the Mditer work. The central idea is that it unifies the object detection and the phrase grounding. So for example, in this here, so for the phrase grounding task, we try to align image regions in the image and the phrases in the text and output the successfully aligned region and the phrase pairs as a grounding result. But remember that here, the phrases in the text is always are always there in the image. So there's no negative sample there. On the contrary, for object detection, we construct a very simple text prompt. For example, for Coco detection, we just simply concatenate the class names in Coco as a prompt, like person and bicycle and then hair dryer. And then we try to align the regions in the image and the class names in the text. Here, this is the important difference because in this text prompt, not all the concepts appear in the image. So there's negative examples. This is the key parts that finally the Glib model can do object detection in a zero-shot manner because it has negative examples in the training. So with this kind of prompt tuning, so the Glib model tries to match the phrases or class names in the text and the regions in the image. The Glib model finally outputs the successfully aligned region phrases, region phrase pairs as a detection result. So thanks to this unified perspective, the Glib model can pre-train the grounding. We can pre-train the grounding model on both types of data, like the grounding data collected by the Mditer model and the detection data, like object 365 or open images via genome. In fact, the detection data, you can see that it's even larger than the grounding data available. Because we can use both of the kind of data. So there's a reason why that the Glib obtained the best grounding model, grounding performance and also the best detection performance. But finally, the problem is that still this is quite small. We only have about 1 million image text box grounding data and 2.5 image text box object detection data. So how to further scale up? So the answer goes to the self-training on massive image text paired data. So you can see that we know that on the internet we have a lot of we kind of have infinite image text pair data like we show it here. What we can do is that if we have a good grounding model, we can just run the grounding model on this image text pairs and then generate pseudo boxes for this for the phrases in the image. So in this case, for example, in Glib, we run a grounding model on 24 image text pair data and this result in 78.1 high confidence phrase box pseudo annotations and 58 unique noun phrases. So you can see there's a notch notch jump in the unique noun phrases compared to object detection data and the grounding data. More importantly, compared with the traditional object detection self-training, the real concept in traditional object detection supervised training just was unlimited to the teacher model, but in the phrase grounding self-supervised method, the visual concepts are significantly scaled up from 2 key concepts to about 6 million concepts. And this concept covers massive visual attributes and relationships, which is not covered by typical object detection data. Second, we observe that the grounding self-training method produce more accurate bounding boxes thanks to the text clues. So after we train this unified grounding model for both grounding and object detection data, then we can just use it to do on downstream tasks on many different object detection tasks in a very simple way. So the use of this grounding model for detection is instead of you only have image as input of the model, you also have the text as input. For example, to detect for COCO detection, besides the image as input, you have the text prompt, detect dog, person, couch, hair dryer, all this kind of classes in COCO. So this, you can think that this is the intention of the user to what kind of objects they want to detect. And if you want to detect smoke in the California mountains, you can just simply construct this simple query, detect smoke. And then if you want to detect fishes in the aquarium, you can construct another query. And finally, you want to detect dog and person in thermal images, you can just simply replace the text prompt, and you do not need to change the model at all. So in this case, we can do zero-shot object detection. And definitely this model can be further fine-tuned to get better performance. So you can see that on COCO, a zero-shot Glib tiny model can achieve 46.3 AP, outperforms the established supervised system, such as FastRCN. On average, again, a zero-shot Glib model can rival with supervised systems. Glib also serves as a strong quick-trained model. When we fine-tune the Glib model on COCO, at the tiny scale, Glib already outperforms the previous SOTA by 5 AP. And if we further scale up the model size, go to the large scale, Glib set a SOTA performance when it was released. But definitely our goal is finally go to object detection in the wild. So to measure how this vision language model for object detection behaviors for object detection in the wild, Glib collects 30 real-world detection tasks. It covers different scenarios like wild smoke detection, mask wearing packages, pistols, and potholes on the road. So we measure the Glib model on this downstream task in the no data region and in the full fine-tuning region. So let's look at this picture. So if we the x-axis of this picture is the amount of training data. There's 0, which means that this is zero-shot transfer. We do not need any downstream task-specific data. And also we have 1 shot, 3 shot, 5 shot, 10 shot. To finally the 4 shot, you use the 4 data in the downstream task to fine-tune the model. The y-axis is the average performance on certain downstream tasks. You can see that Glib shows a great data efficiency performance. A zero-shot Glib model can rival with a few-shot SOTA detector, while a few-shot Glib model can surpass the 4 supervised baselines. And finally, due to this kind of vision language modeling for object detection, we can do something like in NLP literature, for example, for prompt tuning. So here we can see that this is the kind of vision language model, Glib model for object detection. It has the image encoder, language encoder, and the fusion encoder to finally output the object detection. When we face a downstream task, we just as we mentioned just now, we just compose the text prompt for this downstream task, gets the text embedding here. This is the text embedding, and the text embedding is combined with the image embedding to go to the fusion encoder to get the detection model. The interesting part is that when we do downstream task object detection, we only need this prompt embedding part, because for every detection task, the prompt is the same. So what we can do is that we can just tune this prompt, just tune this single green prompt part for the for this specific task, and all the other weights are fixed. So in this case, we can have a single model on multiple detection tasks. Here, with this prompt tuning strategy, we train a single model for COCO and for the other 30 object detection task for OD in the wild. So you can see that for all this kind of tasks, the prompt tuning this single model have very nearly SOTA performance compared with the task specific fine-tuned model. More specifically, we can look at this picture. You can see that still the x-axis is the data number of short data we use. The y-axis is the average performance. So you can see that with prompt tuning, especially for large models, the purple curves on the top, you can see that the fully fine-tuned model definitely perform the best, but it's task-specific model. Finally, for every task, you have a set of weights. But with prompt tuning, you have one model for all the tasks, but the performance gap, you can see it's very small. This coincides with the observing in NLP literature. When you do for larger models, when you do prompt tuning, the fine-tuned performance and the prompt tuning performance gap is very small. So let's return to this existing work. Just now we covered two representative work. One is Mditer, one is Glib. And now we want to show some recent work. For example, for this one, Glib V2, which is to unify localization and vision language understanding. So there are two key parts in this work. One is that this extend Glib to handle both object detection and the traditional vision language tasks. The key idea there is that localization plus vision language understanding is grounded vision language understanding. So you can just train a grounded vision language understanding model for both object detection, segmentation, and also for vision language tasks like VL grounding, visual question answering, and image captioning. The second key component there is that they introduce inter-image region level contraction loss. Remember, for Glib and also for Mditer, the contraction loss is doing in single image. So in this single image, this box is this concept and not that concept. But we learned from the Glib work that for contraction learning to be effective, we should have a lot of negatives. So in this work, in Glib V2, they propose to use the image regions and the concept in other images as a negative example to make stronger contraction learning, to make stronger region word level contraction learning. So if you are interested in, you can check out this paper. And also there's another paper called Fiber, cost to fun vision language pre-training with fusion in the backbone. So there are two key components there. One is that it proposed a two-stage cost to fun pre-training framework for vision language pre-training. The key observation is that for some tasks like real question answering, image captioning, and the image text retrieval, there are essentially no this task is essentially just require global image understanding, and you just need to use no resolution image to do the pre-training, which saves you a lot of computational power. And then some tasks like object detection, face grounding, they are essentially kind of need localized understanding, and you need to use high resolution images to train these models. So this kind of two-stage pre-training categorize kind of different tasks categorize this task into two categories and distribute computational costs kind of very efficiently for different tasks. The second component is fusion in the backbone. So fusion, traditionally we do fusion kind of at the very end. This will result some problem like very kind of it's very slow to do inference. But with the fusion in the backbone technique, kind of the fiber work shows that the kind of the inference speed is kind of as fast as traditional kind of single modality vision models. So finally, I want to talk about some kind of future directions. The first one is large-scale vision-aware pre-training for object detection. So so the question is that how to better use the weakly supervised data, like the image text pairs. In Glib work, we can the Glib work propose a very, very simple way, just the naive, the very basic version of self-training. But we know that this kind of image text pairs contain a lot of information. How to better use that? Like in image classification literature, we have noisy teacher-student learning. We have kind of meta pseudo-label learning. All this kind of advanced self-training method may be useful to better leverage this weakly supervised data. Second, for scalable object, we want to what is the scalable object detection model architecture? So this is currently complex models are quite difficult to scale up to large models, and the people are developing transformer models to build larger and larger models for object detection, like Mditer, but like Diter. But Diter, the now of Diter work is still in the early stage. So how to design this large-scale object detection model architecture is still an open problem. The second point, the second direction is that to focus on zero-shot and few-shot object detection. We know that the traditional academic benchmark like COCO or Open Images or Object 365, they are quite saturated. But if we look at the the data efficient perspective, if we ask the problem that if you are only giving one shot of data, so what the performance is, this is underexplored previously, but with the vision language pre-training get into object detection tasks. So this problem, this data efficient training will be more and more important and more promising. The second one is more training efficient method, like to do full model fine tuning. It's computational cost. It's computationally expensive. Then people propose linear probing or pump tuning as efficient training method. But what's the other efficient training method? So this is also open problems. Finally, is this more efficient or compact model on device? We are in the race of building larger and larger models, but they cannot run on device, on cell phone, on glasses. So how to build this efficient model is a big challenge. Finally, we have in general, we have this problem of computer vision in the wild. We want to extend this vision language approach for more computer vision problems like segmentation, action recognition, human object interaction. All these problems can be formulated in the similar way that ask the question of segmentation in the wild, action recognition in the wild, etc. Another direction is more modalities. We can see that currently we are only studying vision and language modality, but we know that we have video modality, how to do 3D video detection in video to do 3D detection. Also have more audio modality. Sometimes for AR, VR scenarios, we even have other sensors like gravity sensor, IMU data. All these modalities are useful in real case and it's good to model them in. So the final goal is really to build a true multimodal foundation model, in my perspective. And this is the end of this kind of presentation. Thanks.